Okay. This question, this series of questions, I think will help with the first response. So notice there's two graphs for every chart.
Is this like saying it's going like that? Is that the path?
Yes.
Can you draw the path for me? I'm sorry.
No.
That?
Okay. That's all.
You get to that?
Yeah.
So this is a very good question.
Oh no.
Have a conversation.
I got it. Because the field has to be constant. The negative integral. Yeah. And the negative integral. Yes. Opposite sign. So when the field is high, the voltage is pretty sure.
Well, it's also like don't ever say integral. It's going from up to down. So that's all you're doing to say. It's easier for me to say.
Correct answer is A. You have a constant electric field of 90 divided by 0.02 meters. Good with that? From this equation here. Because electric field is constant, you don't have to do, no, you don't want that. You don't have to do an integral. Good with that? And since the field is constant, you have a constant slope. Good with that? Going from a higher electric potential to a lower electric potential. Positive plate to the negative plate. This would be your elevation gain on the landscape. Okay. So now we stick a metal slab in between the two plates.
Is it going through a conductor?
No, it's not. It's not. There's still a gap there, so you're not getting a flow. Is that what?
Are you going like the small path for the conductor?
Yes. So you're going from here to here. Hold off your conversations until people have had a chance to conclude in their own brain independently without being influenced or influencing. Thumbs up when you have something in your brain. Converse.
Half the distance.
Does something have to be a solid or a liquid to be a conductor, or can it be a gas?
It could be a gas.
Is that a thing that exists?
Mm-hmm. Actually, we're going to talk about it here momentarily.
Awesome.
Correct answer is okay, so we're all in agreement with this, right? Okay. So the electric potential stays constant in, and we're all in agreement that the electric field is zero, so the electric potential is constant. Okay. We still need to go from 90 down to 0 volts. But we're doing that in a shorter horizontal distance. So the slope on this thing is going to be steeper, meaning you have a higher electric field. Does that make sense? Correct answer is B. You all right with that? This, let's see, don't want to say that yet. Okay, we could view this. This could be viewed as two capacitors in series with a gap of 0.5 centimeters, so 0.005 meters between each one of those. You all right with that? I don't know if that helps or not. Thumbs up when you have a guess. Have a conversation.
not increased increased charge.
Or I do any questions, I don't know if beta vacuum over data.
It's like 7.
Correct answer is I heard ease, some ease, but didn't hear definitive ease. He is correct. Okay. So we're staying. We're still connected to the battery. So does everybody get the fact that we're still at 90 volts? Okay. So we're gonna knock out B and C is like straight away. All right. With that. Okay. So the electric field in a insulator in a dielectric still exists. It's just weaker. Okay. So um, the fact that this is horizontal says there's no electric field, even though this one says there's electric field. So D is out. Okay. Now, from here to here, you have a weaker electric field. The slope of this is less. So you're, oh, there you go. Okay. You have a weaker electric field. In the conductor, you have a shallower slope. And so you have a steeper slope there and there to make up the difference. So it's going to be more than 4,500, or yeah, to make up the difference in the elevation, but this is still contributing somewhat. So you're not bumping up to 9,000 like you did with the conductor. How are we doing with that?
Sorry.
Because we still need to go from 90 volts to 100 volts. If there was no dielectric, it would go straight like that. That slope would be that pitch, or that slope. But because this part here is shallower, because we have less electric field, we got to make that a little steeper to still get down there in that smaller distance. I don't know if that. Let me try it in a different way. When this is still hooked up to the battery, you stick your dielectric in there. That's going to increase the capacitance, and more charge can get on this plate, which is going to cause a stronger electric field in this gap here. In the dielectric, though, it weakens that field. So it's going to be stronger than your 4,500 in these spots here, but weaker because that dielectric has that internal electric field that's fighting against the outer one. Is that?
Can you show us the map real quick?
Let me. I'll cycle back through that.
If the insulator was touching like both sides, it would just be like there was no insulator.
Good question. So typically, our dielectric's like a sandwich, like it's like a hamburger. you don't ever have gaps in your hamburger. Like you don't have air gaps. It's just, okay, so it's touching. So typically it's sandwiched and there it's a constant whatever that field is. So we don't necessarily get that. Does that make sense? Okay. So this is just, these are fabricated questions just to make you think, which funny, that's kind of what the AP test is like. Yeah. Okay. Oregon. Good thing it's multiple choice. Have a conversation. Tell them why you think so.
How is it voltage like?
Yeah, that's why I'm saying that.
No, there's no like what makes the motor like voltage change. How does it disconnect from the battery? Yeah. So then why does it freeze?
Yeah, it's like the only. But it's not.
It's not, never mind. Ignore me.
What?
Because it feels.
B is not right. Yeah. Okay, go for it. Okay, correct answer is E. E. Electric eels. Okay. When you disconnect it from the battery, what stays constant? The charge. Okay. So when you so you are okay. I'm gonna do two different approaches. In between these two charged plates, the capacitance ooh, I don't know if I want to say that. Let's see. Okay, I'm going to try the other approach. Then we'll see if we can figure out this approach. I'm going to look at it as two parallel plate capacitors wired in series. Okay. In series, the total capacitance decreases. You okay with that? Um, so the charge is held constant, the capacitance goes down, and so okay.
Capacitance goes up. Capacitance goes up because the total distance decreases. On each of those.
Oh, good call. Yes. Oh, shoot, that just got more complicated. Yes. Okay, let's pull that. Let's see what else can we pull out here. That is not an easy answer. Let's see what else can we say. Okay, the charge on this guy is still the same because these things are going to polarize. And if you did a Gaussian surface in here, the flux is going to be zero. The enclosed charge needs to be zero. So whatever the charge on this surface was, this plus Q, is going to be equal to the negative Q on this metal surface there. And you can have the same conversation on the other side, which agrees with capacitors in series. The charge has to be the same in series. Man. Capacitance is equal to, I always forget where epsilon goes. I think it goes up top. So the area is not changing. The gap distance just went from 2 centimeters to a half of a centimeter in each one of those. You okay with that? Ooh. Maybe this might feel cheating. If we just went boom, like push that against there, and so we just have a gap distance of 1 centimeter, and the electric field for a conductor, I just did that, is equal to surface charge density over epsilon naught. So charge over area. The area didn't change. The charge didn't change. Electric field didn't change. Electric field didn't change. We halved, there it is. We've halved the distance. So we have the voltage. Okay. I know that kind of feels cheating because we touched that, but let's say we move it back. We still have 1 centimeter to make that electric potential difference. No. Yeah, we still have 1 centimeter to make that change. We did have 2. So that's why it's 45. 0 on the plate. Okay. From this point of view, we have quartered the capacitance. So we quadruple the capacitance, like going from this original one to these two. We have now 2 capacitors that have 4 times the capacitance. So when we add those together, that's going to cause the charges stays the same. That goes up, right? Because we got 2 over 4c equals 4 over twice the capacitance. So our capacitance goes up, so voltage has to go down. Whew! That was brutal. There's 2 different ways you can do it. Thank you, Griffin, for saving my butt on that gap distance. Good with that? All right, yay. That was fun. All right. All right. So, I already talked about that. So, here's some just practical stuff. We always model like this, but really they look like this. Okay. It's kind of the fruit roll up model, except they have 2 sheets of wax paper in between them. So you're never going to get fruit roll up touching fruit roll up as they roll it up. Actually, just kidding. There's 2 fruit roll ups. That's the difference. There's 2 fruit roll ups, and they need 2 pieces of wax paper, and they roll that up so you don't ever get fruit roll up gunking up with a fruit roll up.
Earlier we calculated like a cylindrical capacitor. Would that be like this, or would that be?
No, good question. This is different. This would be a parallel plate capacitor. The cylindrical things are literally like a coaxial cable. I don't know why you'd ever want a capacitor like that, just to make you think. So on capacitors, they have their capacitance, but they also have a voltage rating. That is your maximum voltage. In the pressure tank analogy, that is where the rubber bladder in there has maxed out. If you put any more like water in there due to a higher pressure than what it can handle, it's like overfilling a balloon. You're like, poof. And so what happens is that that's rated upon the electric field that the dielectric can handle. So when there's an electric field that the dielectric experiences, the molecules polarize. If that electric field is strong enough, you can actually rip electrons off of that molecule, and all of a sudden that insulator now becomes a conductor because you have free electrons able to pass through. This is known as dielectric, no, I think it's dielectric breakdown. They say, like, don't ever let the blue smoke out of the capacitor. That's when you fry the capacitor. There's some labs in college where it's like a circuit lab where you're like, if you fry the capacitor, you fail. And this is like a lab practical exam. And so, like, don't let the smoke out of the capacitor. Don't let the blue smoke out. And there's always one. You hear a pop. That's a semester. Try it again next time. Okay? Because comparatively, a semester out of your pocket is way cheaper than $1 million project out of your company's out of your company's pocket. Like, get it right. Double check, triple check. No pressure. No, really, there's a lot of pressure. But that's what you're getting trained for. Right? All right, so dielectric breakdown happens. There's different electric fields that will cause this to happen. Um, so, James.
So does that mean that under a strong electric field, anything can just be treated as a conductor?
Yep.
Are we allowed to just assume that the electric field is strong enough to make it an insulator or conductor on the AP test?
No. Okay. So, where does an electric field, where is it the strongest on a charged object? If it's like a not spherical, where's it going to be the strongest electric field?
Closest to the charge.
Which would happen where? At points. Good job. Okay. So it happens at sharp curves, sharp edges. Okay. So you get a really high concentration of charge here. You get a really strong electric field. Okay. And so what happens is um, you have an air molecule that's neutral is experiencing a really strong electric field here, and occasionally you get this you get some other outside energy added to it, or maybe it just happens, and it causes the electrons to rip off, and so the electrons will go to this, and now you have a proton, positive ion gas molecule, and um, that's gonna like cause a chain reaction and get this, and so Aiden asked, can solids and liquids are they the only conductors? Could you ever have gas being a conductor? If you get ions, you can get a flow of charge. And in the case of liquid and gas, you can have a flow of positive charge because now we're not just limiting ourselves to electron flow. it could be positive ion flow and electron flow in opposite directions. This is a cool demo. Just thought of this. I don't have the equipment to like. Well, I gotta check out YouTube. This is a.
Hello, welcome to Ludic Science. Today I will show you this interesting experiment of the candle in an electric field. As you can see, the experiment consists obviously of a candle that I'm going to light up, and the candle is between two metal plates. Between these plates, a high electric field will be created because we're going to connect the plates to a high voltage power supply. This little power supply can provide between 10 12,000 volts and is connected to a regular power supply. So we will see what is the effect of the electric field
I feel like I can do
in
that.
the candle flame. The flame of a candle or a lighter, due to the high temperature, creates ions, both positive and negative, in the air. That is, the air is ionized by the flame. It does not become a plasma because the temperature of the flame is not very high. Maybe a higher temperature flame, such as an oxyacetylene flame, which reaches 3100 degrees Celsius. The flame is again vertical and bring the plates together, and
Oh, come
I'm
on.
going to turn on the high voltage power supply, starting at a low voltage. There we go. And slowly increase the voltage.
Come on.
And you can see how the flame starts to distort because of the ion wind present between the two plates. If we turn off the power, the flame is again vertical. Let's turn on.
That was not as cool as I was anticipating. Dude, come on.
Look at that. Yeah. Did you know candle flames conduct electricity better than air? That is because there are ions in the flame, positively and negatively charged particles resulting from the combustion process. It's kind of a plasma, and you can.
All right. Well, shoot. All right. So, anyway, you get this chain reaction and dissociating these electrons, you get positive, you get plasma. Okay. And this is what we see when we see like the Van de Graaff generator going